Calculus, trapezium rule. Trapezium rule is a technique to find the area below the curve for some function that we will not be able to find the integration for them. Some function, it's difficult to find the integral of them, so we are using the trapezium rule. Trapezium rule in this case is to divide the area below the curve or the area you wanted to find. You divide it into small trapezium. A very small trapezium, so the curved part here approximately be a line segment. So you have a trapezium plus trapezium plus trapezium and so on. And by adding these trapezium, you can find the whole area below the curve. Whole area below the curve. Let's first start with example that we can find the definite integration between the point 2 and 3 for the function x power 4. And then we are going to find the area by using the trapezium rule and notice the differences between them. If you wanted to find the integration from 2 to 3 for x power 4, you will start first by find the integral of x to the power 4. You are going to add 1 to the power. You are going to add 1 to 4, so it's going to be 5. And you are going to divide it by the new power, which is 5. Then the limits of the integration are from 2 to 3. So you are going to plug x first with 3 and to plug x with 2 and find the difference between them. As we know, if you are finding the integration of a to b for a derivative of a function by dx, it's equal the integration of the function from a to b, which is equal replacement of the function at b minus replace of the function at the point a. So we can write it like this, that's better. So it's equal f of b minus f of a. So it's 42.2. So the exact value of the area of x to the power 4 from 2 to 3 is 42.2. Now, look at the given figure. I graphed f of x equal x to the power 4. Okay? And point A, I'm going to replace it with the point 2. And point B, I'm going to replace it with the point 3. So I'm going to find the integration from 2 to 3 for x to the power 4 by dx. The one that we calculated a few minutes ago, right? If we zoom in here, you will find that there is a small difference between the area of the curve and the area below the line. The area below the line here to give you the trapezium, right? If I wanted to find the value of this point and the value of that point, which is f of a, and this value is f of b, so it's f of 2 and f of 3. So I can say that for this function, at the point 2, f of 2 is equal 2 to the power 4, which is equal 16. So this point is 16. And this point at 3, so it's f of 3, which is 3 to the power 4, which is 81. Notice that I divided the whole area below the curve into one trapezoid or one trapezium. I divided the whole area into one trapezium. Now, let's find the area of this trapezium. We all know that if I have a trapezium, and I wanted to find its area of this trapezium is equal half the sum of the two parallel bases multiplied by the height. So the two parallel bases here is base 1 and base 2. And the height is the line segment joining between them. The line segment joining between them. So area here is half 16 plus 81 multiplied by the height, which is 1. So half 16, this base 1 is equal to 16, base 2, its length is equal to 81, multiplied by the height between them, the perpendicular distance between them, which is 1. So half multiplied by 16 plus 81 divided by 2 is equal to 48.5. 48.5. So 16 plus 81 multiplied by half is equal to 48.5. So the area, by using the trapezium rule for this function, as I divided into one trapezoid or one trapezium, is 48.5. Look, we said that a few minutes ago that the area or the exact value of the area below the curve is 42.2. But now we are saying that area is 48.5. Is it overestimate or below the estimate? It's overestimate. Overestimate. But it's not close enough. It's not close enough. And I'm going to present to you why it's not enough. Let's divide the area below the curve here into two trapezoids. I have the curve of the function f of x. At the point 2, the height is 16. The whole length here is 16, as f of 2 is equal to 16. 3, f of 3 is equal 81. What if I can divide the area here into two trapezoid, trapezoid 1 and trapezoid 2, or trapezium 1 and trapezium 2. So 2.5 to the power 4 so if of 2.5 is 39.1, approximately 39.1. So I wanted to find the area of the first trapezium plus the area of the second trapezium. Area of the first trapezium will be base 1 plus base 2 over 2 multiply the height between them. And the second area here will be base 2 plus base 1 multiplied by 2, divided by 2, multiply the height between them. So let's find the area 1. So we're going to call this trapezium 1, trapezium 2. Area 1 will be half base 1, which is 16, plus 39.1, multiply the height, which is the difference, which is half, which is equal approximately 13.8. Area 2 equal half multiplied by the first base is 39.1 plus second base is 81. Multiply the difference or the height between them. This width is half. So 39.1 plus 81 equal, divided by 2 equal, times 0.5 is equal 30.0.25. Or we can say it's 30.30. So 30 plus 13.8, we will find that the area here is 43.8. So the area here, by using the trapezoid, total area is equal 43.8. Look, the difference between when you divided the trapezoid into one and you divided the when you divided the area into one trapezium and when you divided the area into two trapezium, we will notice that it's more accurately, or it's nearest to the value, which is the accurate value is 42.2, and now we can say that the area here when we divided is 43.8. So we can say that when we divided the area below the curve into more than one trapezium, accurately the difference of the line segment of the curve here between the curve line and the line segment of the trapezium will be the same. Approximately this length will be the same. Instead of divided the area here into one trapezium, instead of dividing the area into one trapezium, I can divide it into more than one trapezium. And by adding these trapezium, I will find accurately the area of the curve, or the shaded area, the bounded area between the curve and the x-axis. Why we are using that? Because some functions are totally difficult to find the integral of it. Trapezium rule to find the integration of a function, or to find the area below the curve and the x-axis. Okay. For example, approximate area here, this graph is the graph of y is equal sine x. Graph of y is equal sine x. On the interval from 0 to pi. And I wanted to find the trapezium rule for 4 parts, or four sub-intervals, 4 sub-intervals, to find the area, to find this blue area below the curve, or between the curve and the x-axis. So I need to find the area of the yellow shaded part. And the meaning of 4 sub-intervals, that I'm going to divide the area between 0 and pi into 4 parts. 1, 2, 3, 4. 1, 2, 3, 4. Actually, we call them 4 small trapezium. Notice that if I'm going to divide for 4 equal parts, it's equal 5 digits here. 1, 2, 3, 4, and 5. This value, which we called it x naught, and the last value it's xn. Okay, so I can make a small table writing up the value of x and down y, which is actually f of x after replacing the value of x in the function. And I have 5 values: 1, 2, 3, 4, and 5. First value is the first interval, and I can write this integration as integral from 0 to pi for sine x. So 0 is the first value here, and pi is the last value there. Then I find delta x, or we can call it h, the height between the, the height of the, yes, the height between the two values of x. So it's equal pi minus 0 divided by 4 values, which is equal pi over 4. So every time I'm going to add pi over 4. So 0 plus pi over 4 is pi over 4, plus pi over 4, it will be pi over 2, then 3 pi over 4, then it will be pi. Then I plug in 0 in the function. So we know that what the value of sine 0? Sine 0 is 0. Sine 0 is 0. Then sine pi over 4. Sine pi over 4, which is root 2 over 2. Then sine pi over 4. Sine pi over 2. Sine pi over 2, which is 90, and sine 90 is 1. And then sine 3 pi over 4. 3 pi over 4, which is 135. It's root 2 over 2. We are going to find it as exact value. Then finally, sine of pi, which is equal to 0. Then let's apply the rule of the trapezium rule. The rule says that area below the curve by using the trapezium rule is half the height multiplied by y naught plus twice y1 and so on till the last one before y, last term before y, then yn. So it's half delta x or h, the one that we figured it out here. We put it there. So it's pi so it's half pi over 4. First value y, last value 0. So I can write it as y, first value is 0 and the last value is 0. First value is 0, last value is 0. Again, I did the same mistake again. 0 and 0. Then 0 plus twice the values between them, which is root 2 over 2 plus 1 plus root 2 over 2, which is equal half pi over 4 multiplied by 2 multiplied by 1 plus root 2. So can be written as pi over 4 multiplied by 1 times root 2. After cancelling 2 with 2, it's pi over 4, which can be written as pi over 4 plus root 2 over 4 pi. If you wanted to expand the bracket, this is the exact value of the area below the curve. Of course, if you need to find the answer in 4 decimal places or 2 decimal places, you can change pi into 22 over 7 or 3.40. Find in each problem, approximate the area under the curve for 4 trapezoids. The meaning of 4 trapezoids that you are going to define the distance from the 2 points into 4 parts. This one can be written as integral from 1 to 5 for x plus 6. By the way, you can find the integration from 1 to 5 for x plus 6 clearly or without using the trapezium rule. But let's apply the trapezium rule and use the exact value of the integration and find the difference between them. If I'm going to solve it without the trapezium rule, first, I'm going to make integration for x, which is x squared over 2 plus 6x from 1 to 5, which is equal, I'm going to replace x with 5 minus the value of x at 1. So it's going to be 25 over 2 plus 6 times 5 minus, replacing x with 1, we're going to be have plus 6 times 1, which is equal 30, and 12.5 is 42.5 minus 6.5, which is equal 36. So the exact value of the integration is 36. Now I want to apply the trapezium rule. So to apply the trapezium rule, I should find the height. Height is the last value, my last limit of the integral minus the first divided by 4. So it will be 4 divided by 4, which is equal 1. So we insert a table. Here is x and here is y, or f of x. First value, which is 1. Last value, which is 5. And I want to find 5 values because it's 4 sub-intervals. And each time I'm going to add 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. Then I plug in 1 in the function, which is x plus 6. So 1 plus 6 is 7. 2 plus 6 is 8. 3 plus 6 is 9. 4 plus 6 is 10. 5 plus 6 is 11. Then I'm applying the rule. The area is half. H, which is 1. First value of y. First value of y plus the last value of y. So 7 plus 11 plus twice the sum of the rest of the values of y. So it's twice 8 plus 9 plus 10, which is equal half. What is 7 plus 11? It's 18. Plus 18 plus twice 8 plus 9 plus 10. So it's 72. And half of 72 is 36. Notice that area of the trapezium here give me exact value as the area. To add for you more, if you wanted to graph this function, we all know that y is equal x plus 6. So it's a straight line, passes through the point 6, and with a positive slope, and slope is 1. And you wanted to find the area from 1 to what? To 5. Notice that the area from 1 to 5 is exact trapezium. Look, it's exact trapezium. This height is 1 plus 6, which is 7, and this height is 11. By considering this one as a one-hole trapezium, you can say that directly the area below the curve is half base 1 plus base 2 multiplied by the height, area of the trapezoid. Base 1 is 7, base 2 is 11, so 7 plus 11 multiplied by the height from 1 to 5, which is 4. And 7 plus 11 is 18, half multiplied by 4. Half 18 is 9, 9 by 4 is 36. So we figured out the area below the curve using 3 steps here. Graphing, and we find area of one trapezium rule, and using the normal integration rules that we used to know before.